Hello, everyone, and welcome to our workshop. So we are now here at MLVis 2021, the workshop on machine learning visualization for big data. I'm Jaakko Peltonen. I'm one of the organizers of the workshop. Along with me are the two other organizers, Daniel Archambault and Ian Nabney. And I'll first give a brief intro to this workshop, and then we'll get going with the program. So unfortunately, we're not in Zurich, right? So the background here is supposed to be Zurich. So you can imagine that we are in Zurich, even though we are only virtually there. So this is the 6th year that our workshop is co-located at EuroVis. The topic of the workshop is how we can bring together visualization and machine learning so that they can benefit from each other, how visualization can benefit from machine learning and how machine learning can benefit from visualization, and in general, how these two communities can better come together and work together. This was something that arose from an idea introduced in a Darkstool seminar a number of years ago. It was a seminar called Bridging Information Visualization with Machine Learning, and basically one of the action points in that seminar was to try to create a place for people to meet. And now this workshop series has sprung up due to that. So thanks to Darkstool for offering a great environment where ideas like this could form. So today, we are going to have many kinds of content. We are going to have a keynote, tutorial components, and also paper presentations. So the keynote will be by Torsten Möller, and he'll be introduced in more detail in a moment. And then we will have 3 tutorial presentations from each of the workshop organizers. So that's going to cover the first session. We'll have a break then, and then there will be a second session which will contain 2 short paper presentations and a panel where all the presenters will take part. So look forward to all of that. Now, we've had paper submissions for a number of years now, since 2018, and we are relatively selective. And this year we accepted 2 submissions. You'll get to see them in the next session. And we thank all of our program committee members for their great support. There's a list of their names here. We have people from all over, including many places in Europe and Singapore as well. And basically, if you are watching this, you're hopefully already tuned to the right place on YouTube Live, and you can engage with us there by giving comments in the chat channel there. They will be provided to us. You can also go to Discord for more lengthy discussion. And the links to both should be available on the MLVis website, as well as in the EuroVis program itself. And that's enough for me for the introduction. So now let's go on to introduce our keynote speaker, and I now give the floor to Daniel.
Hello, welcome to MLVis. We have an exciting keynote for everyone today. It will be given by Torsten Möller. So Torsten Möller, Professor Torsten Möller, is a professor of computer science at the University of Vienna, where he runs the visualization and data analysis group. He received the PhD from the University of Ohio in 1999 and is a longstanding leader in our community for his contributions to visual data science, as well as machine learning methods in visualization. I've personally known Torsten since he was a professor at Simon Fraser University, and most notably 20 years ago, he taught me my very first visualization course. So we are looking forward to his inspiring keynote on visually supported exploration of multiple objectives. And as a little bit of an inside joke, I need to say, we definitely won't tell Sylvia the next time I'm in Vienna. All right, so with that, I will hand over to Torsten Möller.
Thank you so much, Daniel, for a lovely introduction. Much appreciated. And we definitely shouldn't tell Sylvia, that's for sure. Thanks also for the organizers for thinking of me to tell you a little bit about the research we've been doing in the last little while. I want to tell you a little bit about multiple objectives, and hopefully the connection specifically to machine learning, if not already clear, will become clear very soon. So first of all, a little bit of context and why are multiple objectives of interest and non-trivial, and specifically how do we deal with them. And I would like to propose two models, actually, a discrete mental model and a continuous mental model. And it may be obvious why I'm thinking this way. I thought about the Vis community for a long time, and I think there are those of us here that think discretely, and the other ones that think continuously, and I think they're coming all together here to give new insights, hopefully. And I'll conclude with some conclusions. But I would like to start not necessarily with a machine learning problem, but with a very simple problem. An example, assume that you're buying a used car, you have a limited amount of money available. And of course, there's different types of cars available on the market. And you could say, you know, if you want to have the best car according to your budget, or the least expensive car, let me put it this way. So if price is your only objective here, then you can sort those three cars and you'll come up with the best version. Now, on the other hand, if you'd like to, if you live in Germany, for instance, and you can speed at crazy speeds on the Autobahn, maybe you want to take the one that reaches highest speeds. And again, you can sort all these items in a single list and figure out what the best one is. If, however, safety is your most pressing concern as a single objective, again, the choice is easy. You sort those cars in a single list, you take the one that's on top of it, and you're done with it. Okay, but there may be other objectives as well that you might consider here, for instance, mileage and age. And the truth, however, is somewhere in between. You typically try to score high on all of these objectives, not just one of them, and then the choice is getting a little bit more difficult. So this is a standard problem actually in computational science, which is, you know, the basis of physics, Navier-Stokes equations, Maxwell equations. Designing a car in this particular environment that is cheap, that drives fast, that's very safe, or a plane or a ship, etc. You have to consider trade-offs, trade-offs in the materials you're using, trade-offs in how you're putting the car together, and so on and so on. So this is a constant problem actually in the computational science domain. In the data science or machine learning domain, it's also a common problem. The typical example here would be classifiers in machine learning. In order to evaluate classifiers, so for instance, you know, the famous image classifiers, is it the dog, is it the cat, is it the rabbit? You train a classifier based on an error that it makes. And the error is usually the accuracies in these different classes averaged. And that's how you go about it. And you can now write an optimization procedure that optimizes whatever classifier you're choosing. Other examples of trade-offs of different classes, you want to detect cancer versus non-cancers, binary trade-offs. Image segmentation is the typical example. Which parts of the image would you like to better segment? Is it the bone? Is it the soft tissue? Is it the cancerous tissue? And so on and so on. So you have to consider trade-offs here that are usually then summarized in what we also know as confusion matrices. And just as a side note, there's a lot of exciting work actually happening right now in the VIS community on confusion matrices, how to make them scalable, and so on. That's a hot topic, if you will. So confusion matrices for the simple image classification example are here. You want to classify images in cats, dogs, and rabbits. And everything in the diagonal is correct, and everything in the off diagonal are the errors. And then you usually compute an average of the off diagonal ones, and based on this, you train and classify. Okay. Yeah. So the conceptual framework, my point here is this is a common problem in not just data science and machine learning, but also in computational science. And what we had looked in there is a common conceptual framework that I'd like to discuss. There is a model, and there's various inputs to the model, various parameters that determine the accuracy of the model. There is an output of the model, which is oftentimes a particular class, if you will, and based on or a segmentation or a car that you're designing. And now there's different ways of evaluating the quality of the output of the model or the simulation. Going back to our example of designing a car, the aspects that you might consider about the car is how much it actually costs you to produce it, how fast it goes, how safe it is, the mileage it gets, and so on. And so for each of these, you basically create features. Those are your derived outputs over here that you now use to evaluate the quality of your simulation, the quality of your model in the background. Okay. Excuse me. The same thing with a classifier here, a traditional image segmentation technique that takes a brain scan and classifies its pixels into bone tissue, into soft tissue, cancerous tissue, and so on. And the derivation step is here, how many, bone pixels were mixed up as soft tissue and so on. I'm very sorry. Hopefully I make it through this talk alive. In the consumer case that I started out with, we're usually not so much concerned with the modeling stage. We're seeing the product of a simulation or model that we're now trying to rank and rate. So the focus of my talk, though, is really on the back end here. If I have these many objectives, how do I actually come to a sensible conclusion about actually the items that I'm considering, or even the model in the background? So what I usually do now is I ask into the round, what is the classical way and how to deal with multiple objectives? If you think about this for just a little bit, the standard answer is in machine learning as well as in computational science is weighting. I actually already said that in my talk, that we're taking the off-diagonal entries of a confusion matrix and just average them. Averaging is one particular type of weighting, but in some scenarios, you might weigh some confusions more important than other confusions. So to extend this conceptual framework here is we actually have a weight space to consider. And the way you set those weights will greatly influence the ranking of the items, for instance, the cars that you can buy. And I kind of demonstrated that with this little car buying example in the very beginning. So I hope this point is clear. So, and now, if you consider this complete pipeline together, there's actually two approaches in how to deal with this decision space, either through a discrete mental model or a continuous mental model. Let me try to explain. So I now want to focus on the discrete mental model first. In a discrete mental model, we actually have a discrete model space. There might be several different models to consider, but a finite number and a discrete number. And I might consider just a finite many set of weights that allow me to come up with a particular score. So we consider a finite number of outputs or a discrete model space, and we consider a discrete set of weights. Actually, one has to say here that there is an option actually to do without the weightings. And this is also known as a Pareto front. So if you have two objectives, for instance, price and mileage, that you want to consider, then each dot here is a particular car you could be buying. And in this particular case, there's no point in buying the car number K, because there's other cars in the market that do better. For instance, D does better in both objectives. They do better in terms of price, and they do better in terms of mileage. So the challenge will become to actually find the cars that are on the Pareto front, and sort of you can discard all the gray cars here because there's inferior in all objectives. But you still have to weigh the trade-offs between the cars A, B, C, D, E, F, G, and H. So you're not quite done, but you reduced the number of cars or the number of models or items you have to consider. One of the earliest work is actually by Karenini et al. In 2004. It's called value charts, where the idea here is if you set a particular weighting, and here you're ranking different, in this particular example, you're ranking different countries, and you give a third of the weight to the GDP, a third of the weight to life expectancy, and a third of the weight to education. And again, education is recursively weighted based on different objectives. Now, if you set a particular weight here, you can then add these different aspects together. You can now sort them, and you get a particular ranking out of these different countries. This idea was taken further. Before I go there, let me just take up this example on the cars here. So you want to buy a car, different types of Corollas, Luna, Terra, station wagon, and so on. You evaluate price and mileage, and you weigh those objectives, price and mileage, 50-50. You come up with a particular weighting. And in this particular weighting, the Corolla Luna seems to be the best option for you. However, of course, if you change those weights, you put a higher weight on the price and less of a weight to mileage, then this objective or this weighting changes the best possible car that you can pick. So in this case, it would be the Corolla station wagon. Now, this idea was taken up by Kratzer and all some while ago in a tool that I dearly love. It's called Lineup. It's one of the coolest ideas, in my humble opinion. It comes out of this community where you can actually explore this weight space interactively. Here on the example of universities, if you want to choose what grad school you're joining, you can look at the faculty-student ratio, employer reputation, citations per faculty. You give those different weights, and you come up with a ranking. But the beauty of Lineup actually is you can change the weightings So you can look at a discrete set, a finite number of different weightings, and see, for instance, how the one university, in this particular case, Princeton, for instance, that you are very interested in, how stable it is as you change the weightings of the objectives. See, it sometimes drops in the ranking, sometimes it goes up in the ranking. And it gives you a better idea about the stability and also about the quality of these items, in this particular case, the universities. So, however, again, here we had the challenge of choosing between a discrete set of items or models and a discrete set of weights. In a way, though, this is somewhat not satisfactory because there's no one that tells you exactly what weighting you should consider. And often for us, when we buy a car or choose a university, the weights are kind of sort of a gut feeling. They're not precise and they're an approximate. So it would be actually more interesting to consider a continuous weight space. For every possible weighting, how often does a Corolla Luna actually shows up as the best possible car that you could buy? So in order to answer that question, some colleagues of mine at the EuroVis Center and I developed a tool which we called Weightlifter, actually. So, so with a finite number of weights, you can play this game and change the set of weights and see how it behaves. But the idea here now is that you're actually, there we go, you open up the space of possible weights. In this particular case, it's really easy between price and mileage, and consider it as a continuum. And wherever the slider is actually setting this particular ratio of weights to a particular value. And so what you could do now here is you can look at this continuous set of possible weightings. And for each item, you can actually look at which car comes up on top. And you will notice that for some particular set of weights, it will be the Corolla station wagon. For another set of weights, it will be Corolla Luna. And for another set of weights, it will be a different car. Okay, but now you have more of a complete picture of what actually happens here. The challenge will be is, so with two weights or really one variable, this is relatively easy to reason about. But that's not a real world case. Usually we have more sets of weights. So in this particular case, price, mileage, and age. This one-dimensional slider now really becomes a two-dimensional widget that you want to explore. And we can do the same thing. We can actually explore this two-dimensional space. We can segment this two-dimensional space into particular regions. And those regions will be simply marked by which car will win this race on top of the list. And now, again, if you change your weight within this two-dimensional weight space of three objectives, you get an idea of how stable your particular choice is. So, and this is the idea behind Weightlifter. It allows you to understand the decision stability to the changes that you might put into the weights. Or if your gut feeling of the weights is somewhere 50-50, you know whether you change the weights just slightly, whether the choices that you made will vanish or will, or whether there will be a better decision point. The challenge here is, I showed you this with two weights, with three weights, and how do we deal with it actually with more objectives here. We can always sort of reduce it to a one-dimensional slider by actually looking at a composition of two weights that are fixed between two objectives. So we can reduce the dimensionality of the decision space by fixing some aspects in here. And that's how we actually deal with it in a particular way to scale to a higher dimensional setting. So this is demonstrated here with 3 objectives. How you can now have the one-dimensional slider that lets you explore part of the space in this particular fashion. So scalability with regard to criteria and solutions is really done here through a lower dimensional projection and a lower dimensional exploration of this higher dimensional weight space. So what we can also do is, in this one-dimensional case, we can basically project the importance that a particular car is within this higher dimensional weight space into this two-dimensional aspect to give you an idea how stable this choice actually is in this particular fashion. So yeah. So here you get a projection again of this higher dimensional space onto the lower dimensional space to give you an idea about the stability of the best choice for this particular item, or in this case, this particular car. This allows you to do a localization of favorable weight space regions by probing into this multidimensional space. And this is what the interface would look like. The user, basically here, we're dealing with 5 objectives. On the right-hand side here, we have basically a low-dimensional slice of this 5-dimensional, 4-dimensional space. And here we have a bunch of one-dimensional trade-offs, essentially, with the projection of the stability of the blue model, in this particular case, again, a Corolla linear terra comfort, and how this car behaves as you change the weightings in this multidimensional space. So if you also, there's some highlighting, if you click on a particular car, it gives you a preview in which weight region this particular car might actually end up to be your top choice. Okay. Yeah, and here you can interact with the weights directly by going along the one-dimensional slider between the orange objectives and a combination of the other 4 objectives. Okay. And here you can explore again the second best case for what kind of weightings it might actually become the first choice. Yeah, so the challenge here is also, does it integrate well into a workflow of a company? So here we worked with automotive engineers. So the example wasn't taken too arbitrarily in the longitudinal collaboration over 2 years, and the deployment over 1 month with 4 experts. And the feedback was that the weight space is at first somewhat unfamiliar concept. However, after using it for a while, they incorporated it into their workflow, and it gained them confidence that they would be more confident that they're not missing a good solution in this rather complicated possible weight space or space of objectives. Efficiency gains, it made it possible to have a faster setup of automated optimization techniques. And it allowed them to actually explore the space more thoroughly, and therefore also to consider actually more criteria that they have previously done. So those are some qualitative things. But I don't want to stop here. If you spin this a little further, and so I want to introduce to you a second continuous model. And the second continuous model is actually also, if you don't just have a continuous weight space, but you also have a continuous model space. And that means basically you have an infinite number of possible outputs and a continuous model space, as well as a continuous set of weights. So what is typical? So this is a difficult problem. What is quite typical is people fix a particular weighting, and then through a computationally rather expensive procedure, they find sort of the best model for this weighting of objectives. So here I want to point out that if we fix particular sets of weights, we actually have now a scalar function to evaluate at the end. The scalar function allows you a mathematical optimization approach over the model space and the model parameters. If the model space is very expensive, people here also work with surrogate functions, but that may just be a smaller point. So, but the main point is now a typical scalar optimization approach will lead you to an answer. However, if you focus on the model space, then it's a bit more complicated. Because for every parameter setting, you want to actually, or you could, in a brute force way, explore the objective space separately, for instance, in the way that I just mentioned. However, in both cases, this reduces really to a multi-dimensional scalar function understanding. And the example that I want to bring up here is the loss function of a neural network, actually. If you have a neural network, it has lots of different nodes and therefore weights. And as you change those weights, of course, the loss or the error function during the training of the network is impacted. And it's impacted in a scalar fashion. And so that's why, you know, the typical gradient descent methods work for these neural networks. However, if you only consider one weight or one parameter, actually, then everything is a nice scalar function. And in 2D, that's still somewhat easy. You can use a heat map, you can do contour plots to basically look at the scalar function and understand what's going on. And this is also based on some work by Lee et al. There's a typo, it's an autocorrection, it's not, sorry, Lee et al., it's correct. Visualizing the loss landscape of neural networks that was published at NeurIPS 2018. They have very much focused on looking at two parameters for neural networks. That's specifically meaning two particular nodes in a neural network. And as they were changing systematically those nodes and let every other node to be constant, this is sort of the loss function that they see here shown as a height map. And they're comparing skip connections versus, or without skip connections and with skip connections, and the impact it does on the optimization procedure of this neural network. And they argue that with skip connections, it's a much better function to optimize, which a much better behavior. And they simply see that visually through this type of visualization. If you have three objectives, if you have three parameters that we vary, you might be able to still look at it through volumetric rendering. However, it is to be argued that's rather difficult. And oftentimes we actually want to scale to way more nodes in the neural network than just 2 or 3. So multi-D here is hard. And in the visualization community, one of the typical approaches here to deal with multidimensional scalar functions is actually topological approaches, whether it's topological spines, contour trees, or the work of Gerber and all for looking at high-dimensional scalar functions. I would argue that these type of visualizations, these topological approaches, are very helpful for many different use case scenarios, especially if you are interested in extremas, as well as their relationships and so on. But I would argue they're less helpful for understanding the distribution of data locally and the shape surrounding the extrema. And that's exactly what's important for optimization techniques. They're less helpful for shape analysis, cluster analysis. Are there, for instance, areas with a similar shape, as well as for correlation analysis. And so far, I would argue these ideas, and I think there's potential here, they're not so much explored yet for understanding loss functions or, in general, neural networks. Our approach here is going back to Van Wyk and Van Leer and their hyperslice approach from 1993, where the idea is if you have a three-dimensional scalar function, one way to look at it is to simply look at slices. You have a focus point, and through this focus point, you put a 2D slice, and that gives you sort of a matrix of these slices. We have done that in a work that we call Tuner, where we actually explored computational models, in this particular case, a segmentation model. And here we could also deal with multiple objectives by looking at two 8-dimensional scalar functions through the slicing approach, where the brownish one is one objective and the purple one is the second objective. Again, this actually leads to very complex visualizations, but still helpful visualizations, but it doesn't scale all that well either. So slices here are good for reading of function and values, for filtering, find extrema as well in context, though, to really understand the shape, which was sort of our motivation, to understand the range and distribution of values, and for also understanding outliers. However, 2D slices have a lot of problems. They take a lot of screen real estate. There are a lot of axis combinations, and they cannot be overlaid. And that actually lets us to explore one-dimensional slices, which we call Sliceplorer. And here, if, for instance, if you have a two-dimensional function, and you have a focus point, this red point here, you can do a one-dimensional slice in the x direction, which you can show in a one-dimensional graph view here, and a one-dimensional slice in the y direction, which you can show on a second graph here. And the beauty of that is now you can overlay those one-dimensional slices quite easily, and it basically gives you sort of a multi-dimensional projection down to this 1D view, that gives you an appreciation of the global behavior of that function, not just the local behavior as before. So, and this now scales to multi-dimension as well. So if you have a 4-dimensional function, instead of 2 slices, you would have 4 and 4 graphs that lets you explore this. And again, you can overlay. So for this 4-dimensional function, you now get a global overview of this 4-dimensional function, get an idea of what is going on. The challenge, I admit, is of course now the exploration and the interactivity in this particular setting, which we're currently exploring. But it allows you to also observe optimization algorithms, which is the big thing for neural networks, is what is happening actually at an optimization procedure. So you can see whether something gets stuck in a local minimum or whether there's actually global minima that it's missing or not. Okay, so in this particular case, it gets stuck in a local minimum. So we applied this here, for instance, on sort of a standard machine learning data set, the Bostinghausen data set. And we trained a simple neural network with 1 layer and 26 nodes, as well as a 2-layer network with 5 + 3 nodes. We also trained a support vector machine with a polynomial kernel and with a radio kernel. And now we can sort of observe what kind of regression model we have come up with. And we see actually some similarity between neural networks, single layer 26 nodes, and a support vector machine with polynomial nodes, and a 2-layer network with a radio kernel SVM. So we're currently exploring this in the sense of the work of understanding loss functions. And here's our current setup to interactively actually explore this. What you see here is these are all the slices that have been sampled for the weight. So this is a simple network with 2 nodes, I should say. And here is the weight 1, here's the weight 2, and here's the weight 3, and here's the weight 4. And each of these guys show you all the slices when all other 3 weights would be constant, but I'm just changing that 1 weight. And what I'm showing here is the loss function. And so there's some interactive tricks in how we're exploring this. Further, you also see 2 random directions. This was the principal idea behind the paper by Lee et al. From NeurIPS 2018. In this view, to get a 2-dimensional, in this case, heat map of this loss function. And this is currently what we're approaching and working with our mathematical domain experts to help them understand also more complex neural networks. The scalability to real neural networks with millions of weights here is challenging, and we're working on this. So yeah, this is really the model space focus that we're working on right now. Another approach here, of course, would be a multi-dimensional continuous Pareto front to explore the space. This is really equal to multi-dimensional polytopes. And here we have developed a hyperslice explorer. And the idea, we're going back to 2D slices, but we're now slicing actually polytopes in multi-dimension. And let me just demonstrate that to you with a proof of concept. So we all know what a 3-dimensional sphere looks like. And here on the left-hand side, you actually see a 3-dimensional sphere in this hyperslice thing. So we have every 2 combinations of 2 axes. There's 3 combinations of it, and we do several 2D slices in this direction of the sphere. They're all round, of course. By the way, this wasn't a perfect sphere. This was a discretized sphere, so the slices are not perfectly round. The beauty of this approach, however, is that it now scales to higher dimensions. So here we're actually seeing a 4-dimensional sphere, and here we're seeing a 5-dimensional sphere. Again, our intuition works. The slices are round of various sizes. So the intuition works. A little bit more complicated example would be an octahedron. Here's a 3D octahedron with a bunch of slices. And again, the intuition works. And this is interesting because the intuition also works for a 4-dimensional octahedron, which is known as the 16-cell. Which previously the standard way of looking at it is called a Schlegel diagram, where the 4-dimensional polytope is being projected down to 3 dimensions. And here we can now actually look at the 5-dimensional octagon. And again, our intuition works. But this would be impossible to look at through Schlegel diagrams. Here we had done a particular exploration of an application where people were trying to understand the shape of Bernstein polynomials that are all positive. And the question was the coefficients. Is there a particular structure of coefficient space And we can do that for cubic polynomials, which is really a three-dimensional space, but we can extend that to quartic polynomials and to quintic polynomials. And there are particular features that can be observed here that were interesting for our colleagues in mathematics or in computational science, to be precise, to understand what is actually going on. So this brings me to the end of the talk and to some conclusions. Hopefully, I could have you appreciate that dealing with multiple objectives in general is hard, but it's also an interesting problem. And I'm arguing specifically here that a proper approach to understand the space of multiple objectives very much depends on your mental model. I have suggested here to go along the lines of discrete versus continuous. Do you have a discrete weight space or a continuous weight space, or a discrete weight model space or a continuous model space? That impacts a lot how you look at this optimization problem. And I also hopefully communicated there's some really interesting challenges. Lots of people also in the Vis community are trying to understand neural networks. One particular approach that we're looking at here is through this loss function and through this high dimensional slicing, which seems promising, but a little bit more work needs to be done. The discrete to discrete mental model is really governed by these ranking approaches and a Pareto analysis. The discrete to continuous space is governed, our contribution here was the tool called Weightlifter. I think the continuous to continuous mental model is of interest to lots of people, but there's very few approaches in here. And I think there's opportunity to do more research. I think the topological approaches haven't been fully explored in this space and ought to be done. Our approach is through these slices. However, I think there's lots of cognitive challenges that we're all aware of with exploring high dimensional spaces or multi-dimensional spaces, that is. Last but not least, I'm really grateful for a lot of people that I have been working with on this topic. The Weightlifters, which is a collaboration with EuroVis, the Johannes Kepler University in Linz, and University of Vienna. Some affiliation have changed. Many of you probably know Harald Piringer. He just started his own company, Visplore. If you don't know it, you definitely should check it out. They're doing some really, really awesome software. Please check it out. Tom Weir graduated from the University of Vienna, but has now joined just recently EuroVis. And Mark Streit, who's also one of the guys behind, and which inspired some of the work actually behind Lineup. The tuners is again Tom. Stephen Bergner, who is again or back at Simon Fraser University, Ahmed Saad of SFU, but also a collaboration with the Zuse Institute in Berlin and with MPI in Dresden. And the hyperslice explorers here, again, Tom and Michael Sedelmeier, who's now a professor at the University of Stuttgart and cranking out lots of great work as usual. Here's a few more references to the work that I presented here. And of course, I'm happy to take questions, and I thank you for your attention and your patience. Thanks.
Okay, thank you very much, Torsten, for that inspiring talk. We now can open the floor for extended questions. As a reminder, you can type your questions into the Discord server. So with your free registration, you need to log into the Discord server and post your code, and then you can type questions into the MLVis chat. You can also log into YouTube Live and type your questions there. So we do have one question from Helwig Hauser. As always, very interesting to listen to you, Torsten. Thank you. You really talk about a wonderful spot in a research field, providing a lot of challenging and open questions to work on, I think with many open ends. For example, when we are not only interested in the one optimum, but a ranking of a set of the best candidates over multiple objectives. Which of these open ends do you think should be addressed next, given multiple objective functions, feasibility, relevance, etc.? Of course, and then there's 3 dots. Just let me check the Discord. Oh yes, relevance, of course. That's the end of the question.
Hedvig, I mean, you have done a lot of work along those lines. You might even be better fit to answer that question yourself. I think I agree with you. I think there's lots of open ends. And personally, in this talk, I do want to just give attention to not just always. Let me start a little differently. We're very quickly, if we do any machine learning training, especially in classifications, we always optimize the average error, or almost always. And I just say, be careful. That might not be the best thing. That was point 1. Point 2, I will argue that this idea with multiple objectives, as well as with actually a continuous model space, I don't know whether that was clear in the talk. I don't have a good grasp over it. I don't think, let me just say, I don't think many people do, or anybody does, because it's just so challenging and difficult. And I just wanted to spotlight this and say, I think there's a lot of interesting work that can be done. The one particular case that we're working on, it's a very particular way of or very particular setting of this problem, is we're helping mathematicians come up with new optimization functions for efficient training of neural networks. And for them, they needed to get an intuition what the loss function looks like and how the loss function is impacted by particular choices. Simple ones are architectural choices. How is the loss function impacted by different layers, or many layers versus few layers, and lots of nodes versus few nodes, sort of what is happening there. But the colleagues at NeurIPS, they're looking at skip versus no skip connections. What impact does that have? And there's other training aspects, of course, you can do here, where the question is, how is the loss function impacted? And that will greatly impact how quickly or how slowly a particular optimization technique converges to a solution. And there's still little understanding, I would argue, and this is our particular approach that we're focusing on currently. But I think in this space, also in computational science, there's lots of specific problems that haven't been tackled yet, and I think there's room for more work and for more ideas. I hope that helps a little bit.
Thank you, Torsten. As a reminder, questions both in the Discord and on YouTube Live. I see another question. This one from Leo Sperling. Thanks for the talk. I was wondering what the upper practical limits of the number of weights that you can explore in the presented applications.
The typical answer is depends. Depends on what you mean with weights at this particular case. To be frank, I kind of changed my notion of weights a little bit. In the beginning, I was referring to weights in the weight space by weighting different objectives. And in the end, I was actually referring to weights as nodes in a neural network. And those are two separate aspects. And I apologize, I should have been more careful in making that distinction. Now, let me answer your question in both scenarios. In terms of objectives and weighting those objectives, we have dealt with in the order of up to 10 objectives, and therefore up to 10 weights, or 9. It's always n-1, but and I would argue we're somewhat comfortable exploring this. And I personally haven't worked too much in more than that. But there are scenarios with more objectives, and but I don't personally have practical experience in it, so I'd be careful here. For number of weights for neural networks, I mentioned that this is sort of work in progress. We are absolutely certain that we need to be able to scale this visualization and this approach to really hundreds of thousands of weights to be practical for actual real neural networks. And this is a challenge we haven't answered yet. We have some ideas on how to do that. The brute force way, or the classical way to try to deal with this, is to actually do some kind of clusterings of these slice spaces, and therefore basically going to a reduced view where you don't see all the slices per se, but you see clusters of slices and representatives of these clusters. We believe that this approach might be helpful for scaling up here, but we don't know the answer yet. So I have to see.
Okay, thanks, Torsten. We have a question from Michael Optit on the it was originally on YouTube. But what do you think of more qualitative approaches like topological landscapes, Osterling, Schumann, TVCG 2013, that summarize multi-objective main characteristics, local optima, and connections and such?
I have a two-tiered answer for this. First of all, I'm amazed what some of the people have done in terms of topological approaches in this realm. The three works that I really like, I quoted here. For me, topological spines is one of the classical things that, for me, one for the first time actually made topological approaches accessible and understandable. You may or may not know that I have been involved with our good colleague Hamish Carr on weave graphs and contour trees. That was always tangible to me. And I would like to point out that I'm really proud of Julian Turney, who just recently got an ERC grant for the further developing of topological tools in this realm. I think that's one of the few ERC grants in the visualization community. So, I mean, amazing stuff. I'm really proud of these achievements of those people. My second level is, I must also admit, I'm squarely a continuous person. And for me, topological approach has always been very mysterious and hard to wrap my head around. So I really would like to see some of the people with the topological mindset to come up with some interesting solutions. I'm sure they're there here. I personally probably will be more productive to approach it through these sort of continuous slicing approaches and see how far we get on that end to make come up with interesting ways of understanding this really difficult problem. I think this problem needs both approaches. I think I'm better in the more continuous approach, and other people will be better in the more topological approaches. And I'm sure they're already working on it, or yeah. So I think there's lots of room for innovative stuff here.
Okay, thank you, Torsten. Leo just says thanks for the answer. And again, please, any questions, just type them in the Discord or on YouTube Live. Okay, so we got a question from Jaakko Peltonen. Thanks for the great talk. I wonder if you could talk a little about what kind of support there could be for dynamic scenarios where the set of objectives and their weights is changing over a training process or later during the model's lifetime.
Mm-hmm. That's an interesting question. There's also two answers. I think what you're really aiming at, I haven't thought much about, and I don't know what I can give you insights. The other answer, though, is so what we're doing with the way we're producing these slices is we're keeping all weights of the neural network fixed except for one. And so when we change this one node, this one weight, that traces out this curve, this one-dimensional curve of the error. So there is change in weights included here. And if we're doing two-dimensional surfaces, there's two weights changing. Now, granted, this is two weights out of many. Fair enough. It's a very low-dimensional view, and that's one of the drawbacks here. Yes, but my big but to this is, by doing this for every weight, I get a sense of the global view. And this idea of the beauty of the one-dimensional slices, although it's only one-dimensional, I now can have many slices that are overplotted on one graph that gives me a global view of this loss function. And that I cannot have with two-dimensional slices. So this is the one, for me, really lovely little advantages of 1D over 2D that allows you to explore global. And so you actually see what the loss function does when all the different weights are changing. Okay, now if there is changes happening in say the architecture of the, if you go from 2 layers to 3 layers, well, that's a very, very difficult change to compare. That's sort of a discrete change that the only answer that I have for this right now is you plot one and you plot the other next to each other on the same screen and you compare. That's not a great comparison, perhaps, but I don't have a better, for any sort of structural changes to the network, I think that will be difficult to incorporate. Let me put it this way. But there may be smart ideas along those lines. I don't know.
Okay. Thanks, Torsten. Michael Opetit adds a comment that mixed approaches are the future. So thank you. So we have sorry?
He's probably right.
He's probably right. So we have agreement. That's very good. Okay. So we probably have about room for one more question. If there are any burning questions, please don't hesitate to type them either in the YouTube live chat or in the Discord. We're monitoring both of them. Helwig is very happy that you're alive, Torsten, and that you made it through the talk alive. I saw that it was very touch and go there for a moment, but I'm glad you got over your coughing fit.
Note to self: next time have a glass of water next to the talk.
Okay, so that brings us essentially to the top of this session. So how about let's thank Torsten Möller again, and then we will quickly transition to the first of our tutorial talks from the chair. Thank you very much, Torsten. It was very great to host this talk, and it was an interesting, very interesting contribution to the workshop and the community in general. So thank you very much.
Thank you kindly for having me. Much appreciated.
Hello, welcome back. This is the first of our tutorial talks. Our first speaker will be Ian Nabney, and he will be shortly giving a presentation on visualization of mixed data types. So without further delay, Ian.
Okay. Thank you, Daniel, for that introduction. I'm just trying to dig out my pointer. Right. So what I'm going to talk about in this very brief talk is a topic which is, I think, quite important, but very much underrepresented in the literature. The topic I'm going to talk about is visualizing mixed data types. And here by visualization, I'm going to be mainly talking about dimensionality reduction or data projection. And it's quite something when you do a Google Scholar search, as one can do these days. If you put in visualization of mixed data types, there's virtually nothing. There's about 2 papers on this topic, and yet a very large number of data sets that we're interested in have both continuous and discrete data in them, and we're rather missing a trick, I think, here in terms of how we manage them. So an example of a mixed type data set would be, for example, a hospital's patient record system, where the files will include variables such as age, which is continuous, gender, which is binary or indeed non-binary these days, test results, discrete or continuous, height, continuous, and so on. Another good example of this would be census data. So a lot of data sets which are about people tend to have quite a mixture of different sorts of attributes that we have to deal with all at the same time. So how do people actually do this in practice? Well, there are a number of ad hoc solutions which are used to analyze mixed data type data. One thing that people can do is convert all the discrete variables to some sort of numerical scoring equivalent. Of course, the disadvantage of that is that there's an implied ordering on those variables once they've got a numerical score, and that ordering is not justified by the original semantics of the variables that we started with. Or we might consider continuous variables as discrete variables by applying some grouping criterion to them. So these 2 methods are both about trying to convert all the data to be of one type and then applying some method that's suitable either for continuous or discrete variables to that data. And in both cases, it has unwanted side effects. So in the first case, we're introducing additional semantics, additional ordering on the variables, and in the second case, we're removing fine levels of detail from the continuous variables. A third approach that's used often is that both types of variables are analyzed separately, and then somehow we combine the results using some criterion. Actually, having just had a talk about multi-objective optimization, I guess this is an example of that. But ideally, we wouldn't be doing this. But these are all involve various degrees of subjectivity with possible loss of information, and they're not very satisfactory because we don't think that we're splitting people apart into. We don't think that when we're studying individuals, we're not saying, well, we can only analyze this part of the data in one way because that's how it happens to be recorded. That's clearly not a very good way of doing things. So the ideal general solution for analyzing such heterogeneous data is to specify a model that builds a joint distribution from the data with the assumption of an appropriate distribution for each type of feature. So for example, if we had continuous features, we might want to use a Gaussian distribution or perhaps a mixture of Gaussian distributions. If we have binary features, we might use a Bernoulli distribution, and we might use a multinomial distribution for modeling multi-category features. We then have this single model that combined the appropriate density models for each type of variable and then fit the model to data and draw inferences from that. But what we're doing is we're considering the whole set of data, the whole set of variables at the same time. So another way that people address this in visualization is they use topographic models, so models based on distances between data points. So what we're doing here, this is a non-generative way of performing dimensionality reduction, and you might think of T-distributed stochastic neighborhood embedding or UMAP, for example, as two examples where we're using this topographic distance. And we would consider a distance in continuous spaces using the so-called LP norms, like the ones here. So we would say that we have each value, each dimension. AK here is take the absolute value, raise it to the pth power and take the pth root. And then the distance between 2 points is the p norm of the difference between those two vectors. So in continuous spaces, we have a distance norm there. For discrete spaces, we usually just look at equality. So either two values are the same or they're not. If they're the same, then the distance is 0. If they're not, then we have some sort of maximum distance between them. And then we have a question about how do we weight these various different distances together, but we can produce a single distance metric for the whole space. And we can then apply topographic methods such as I said, TSNE or UMAP, though it's worth pointing out they do have an assumption that there is a manifold underlying the dimensionality reduction, and manifolds don't really work in discrete data spaces. So yes, one can apply them, but there is already a slight problem with semantics. There are other limitations of topographic models, and what we'd really like to do is to at least have available a variant of this which is based on probability theory and statistical pattern recognition. So we'd like to be able to apply probabilistic models to this problem. However, we run into a very immediate problem, and that is there is no multivariate distribution that can directly model correlated random variables of different types. Now, our assumption is that there will be some correlation because the reason we're interested in doing this as a single model is that if we assume independence, then we might as well just analyze the data in separate groups. So we'd like to be able to model these correlated random variables, but there is no joint Bernoulli Gaussian model, for example. There is no way of modeling those two things jointly. However, there is a possible way of jointly modeling discrete and continuous variables by using a latent variable approach to capture that correlation between features of different types in combination. And what we'll do is have this latent space, which will be continuous because we'd like to visualize in it, but have different distributions for the different types of data. And although the distributions are conditionally independent in this framework, when we integrate out the latent variables, we get the correlations that we want to see later. Now, this all is very complicated, and I don't want to go into lots of equations here. I've got a picture. I'm not very good at drawing, so I'm never going to win any prize for graphics, I'm afraid, and that's a terrible admission to make at an information visualization conference. But the basic idea is shown here. We have a latent space, hidden space, which is two-dimensional. This is going to be where we visualize the data. But we start off by thinking about this as a generative model. How can this model generate the data that we see? So we have a nonlinear transformation to a continuous space represented as 3 variables here, where I have a Gaussian distribution. So lots of little Gaussian blobs to model the data in this higher dimensional space. And on the left-hand side, I have a discrete space. I have 3 variables, Z1, Z2, and Z3. They're all binary. So what I'm doing is I'm mapping each point here to a probability between 0 and 1, represented by this grayscale here. So if you like, Z1 is nearly 1, and Z3 is nearly 0 here. And so we have a Bernoulli set of random variables over here for the discrete random space, so the discrete space. These 2 spaces are independent when we consider them conditioned on what's going on in this space here. But when we invert this model using Bayes' theorem, we get correlation. We get links between what's happening in the Z space and the Y space. And that gives us a visualization that takes account of both the continuous and the discrete variables at the same time on a single visualization. So this generalized GTM, as we call it, so GTM is a generative topographic mapping, which is the right-hand side of that picture. It works with any distribution from the exponential family for a noise model. We can use the standard EM algorithm to train the model. we have to write down a new set of equations, but they're fairly straightforward to do. We can handle missing data in this framework, so we can do inference over missing data, and we can also compute the importance of each feature as well, no matter whether the feature is discrete or continuous. So compared to what we can do with topographic methods, we have a number of, if you like, extra goodies that we have to hand here that are not available for TSNE and UMAP and so on. So this is a reason to look at this particular approach. And here is a set of data that comes from one of the standard data sets. It's a credit approval data set. We have 653 data points. There are 6 continuous features, 4 binary features, and 5 multi-category features, which we model with a Gaussian, with a Bernoulli, and a multinomial distribution, respectively. And we have here 3 different maps. We're projecting that data down to 2 dimensions. We have here the GTM with just the Gaussians, which doesn't help us very much. The red and the blue are 2 different classes for good or bad credit risk. The generalized GTM, which gives us more information. And then when we apply feature selection as well, where we look at trying to select only the important features in this model, we get quite a rich representation of that data, which tells us a lot more about the relationship between the good and the bad credit risks in that space that we've managed to achieve through this approach of taking variables as they say they are, taking them at their real type, and then modeling them with appropriate probability distributions. And here is a picture of the feature saliencies that we get out. So here the graph runs from 0 up to 1. So 1 is a very important feature, 0 is an unimportant feature. The continuous variables are here. The error bars are because we replicated the experiment multiple times. So continuous variables are roughly in the middle. A couple of them are really quite strong. Binary features are all positively represented, and actually in this particular case, the multinomial variables have relatively low saliency and therefore can be removed from analysis and gives us that much richer visualization plot that I showed earlier on. And on that point, I will stop. I think I've taken just about 10 minutes, perhaps a little more. But thank you, Daniel.
Thank you very much for your talk, Ian. We have probably just about a minute to handle 1 or 2 questions. So if you would like, you can type them either in the Discord or on YouTube. So do we have any questions with respect to the talk? I see some active bubbles on the Discord, so something's about to come through. Let's all wait. Okay, so Helwighauser says, I assume that normalization also gets more tricky with mixed data. What's your approach?
Well, you're absolutely right, and that's particularly important for the distance measures. So that's sort of what I was alluding to when I said about weighting them. The advantage of considering them as distributions is that normalization is done for you in that sense, in the sense that they are all probability distributions considered in the same way. Clearly, we've got nonlinear optimization going on here, so we have to do a little bit of normalization, for example, all to the same mean and variance to enable us to do the optimization, because as with any highly nonlinear model, if you have very strongly different ranges for each parameter, you tend to find it difficult to find a good solution. But the principle of the normalization is already there in the probability distributions.
Okay, thank you. So we'll probably have to quickly stop there because of interest of time. But if you have further questions, remember, you can type them in the Discord, and Ian can get back to them after the session and during the break. So definitely continue typing questions from any of our talks today, and they can be answered at other times. So our next speaker would be Jaakko Peltonen, and he will be speaking on. Yep.
Hello. So I thought that I would give something which is a little more like a tutorial, really. So I'll try to do a quick run through through dimensionality approaches, dimensional introduction approaches, and how they can be used to build various kinds of interesting visual interfaces. So let's see what kinds of things we have in store. So I start from rather simple things, and then I go to more complicated stuff. If you know your dimension introduction stuff, this is familiar to you. If you don't, then now you get to hear about it. So basically, why dimension introduction is needed in general is because high dimensional data, as we've already heard, is kind of hard to explore thoroughly. So we need methods that can help us reveal dependencies between variables that are hidden, and to quantify importance of variables and their combinations, reduce overfitting when we're doing the learning of the models, to reduce storage, memory, data transmission, and basically for us humans to make it just possible to get our hands on some insights about the data. In practice, in some cases, we can also have a situation where we don't have handy coordinates that we could explore, and sometimes dimensional introduction can build those for us, starting from some other kind of observations like distances or neighbors or something like this. So there are usually two kinds of approaches, feature selection and extraction, and I'm mostly focusing on the latter kind. So out of the linear methods, PCA, principal component analysis, is the most well-known one, usual textbook method taught everywhere, and it's basically just finding a transformation, a linear transformation, orthogonal axes that would somehow contain out of high dimensional data to maximal amount of variance. And you can also say that same thing in a different way. You can say that it minimizes the error of reconstructing the data in the high dimensional space based on some low dimensional representations. This is something people like a lot because it's so simple. People can do it using just some eigenvectors of covariance matrices, very easy to do in 2 lines of code, but it has a number of problems. We'll come to some other ones, but basically it's affected by scales of the variables, affected by outliers. So there are some downsides, but there are also some links between PCA and other models that some of them are done through the generative approach, where PCA is represented as a kind of generative model where you have some directions where the data is mostly generated plus some noise on top. This is a purely unsupervised method, so it can't make use of any annotation, class information. So because of this, there have also been developed a number of supervised methods. I'll come to some more complicated ones, but I want to mention maybe the most simple supervised method, or one of them, is linear discriminant analysis. It's something that tries to find directions that don't just contain maximum variance, but directions that try to maximize scatter between categories of data and simultaneously minimize the amount of scatter between the data points within each of those categories. This is also something that people like a lot because it's so simple. You can do it still as an eigenvalue problem, and that's now based not just on one covariance matrix, but 2 different kinds of matrices, a within class scatter matrix and a between class scatter matrix. And basically you want to find a direction where the projection of the within class scatter would be as small as possible, and the projection of the between class scatter would simultaneously be as large as possible, as captured by this ratio. So this is something that can separate classes much better than PCA can in many cases, but this is still just linear. So the problem is that we are mostly dealing with nonlinear problems these days. So we're dealing with manifolds, which already were brought up in the presentations. So it's like a sheet of paper twisted into a shape that lives in the high dimensional space, but is itself inherently lower dimensional. So in order to deal with those, you need methods that can find and unfold the lower dimensional manifolds, but you also need to find ways of estimating that what is the dimensionality of that manifold. There are a number of approaches for that. One of them is that you just divide your data into subsets, and then you do PCA within each subset, and basically then estimate how much dimensions does PCA need within each of those subsets? If you can find that out for each of the subsets, then pretty much you've estimated your dimensionality of your manifold, and you can try unfolding that. So how would you unfold that? Well, there are many nonlinear dimensional reduction approaches which have basically a lot of mathematical representations, a lot of different properties. This is kind of an ill-posed problem. There are so many ways you could go about it, is that there is no one true perfect solution. It depends on what information is relevant to the person who is doing the reduction. So it depends on the domain, it depends on the situation, the task. So I'll mention a couple of different approaches. One of those is that you can try to work with distances and try to see that whether you could find a low dimensional solution that would preserve distances in the low dimensional space to be as close as possible to the higher dimensional original distances. Multidimensional scaling is the most famous approach that tries to do exactly that. Came from psychology. People did, for example, experiments on perception of colors, and then they tried to find coordinates for the colors that would correspond to people's perception of their similarity. These pictures are from some experiments that were done for that purpose. Now, multidimensional scaling is something that is just taking a bunch of distances between pairs of data points, and then it is trying to organize the locations of data points in a low-dimensional space so that the distances in the low-dimensional space would be as close as possible to these original distances. This is something that you can do. You can optimize that iteratively with various approaches. It takes a while to do that, but you can get nice solutions. And there are a whole bunch of different extensions of the multidimensional scaling approach. I'll mention a couple. One of them is isomap, a famous method published in Science. And the idea there was basically just that, okay, let's do exactly that, multidimensional scaling, but instead of trying to preserve the original high dimensional Euclidean distances, let's take another kind of distance in the high dimensional space. Let's take basically a geodesic distance that tries to follow the path of the manifold in the high dimensional space. And then let's try to preserve those geodesics in the low dimensional arrangement of the data points. Turns out that this works pretty well in unfolding those manifolds in a lot of cases. So isomap was pretty successful. But then other people said that, okay, maybe we don't need to focus on all of the distances equally. So a couple of approaches tried weighting which distances were important to preserve. Salmon mapping tried to say that, okay, let's emphasize, let's weight up the preservation of the distances that were small originally in the original space. Curvilinear component analysis tried to weight up distances that are small in the final display. Both of these basically say that small distances in the one space or the other are the important ones to preserve. Now, if you're working with small distances, then you might say that aren't small distances basically distances between neighboring points? And yes, this concept of neighborhoods then became pretty important in a number of methods. Self-organizing maps were one famous method that were based partially on the concept of neighbors. I won't spend a lot of time on that. Basically, it's still something that continues to be popular in some analytics applications. And it is something that can map data to a grid of predefined prototype units with some iterative approaches. And after you've done that, you can summarize the data points at their corresponding units on a regular grid. But another approach is to try to still organize data points onto a low-dimensional space, but do that based on neighbors. So you have some definition of which points are neighbors, either hard neighbors or soft neighbors. And then you try to say that, okay, I would like to arrange points so that the same points are still neighbors in the low-D space. There are probabilistic ways of defining those neighborhoods as well. This is one example with a probabilistic input neighborhood. This is a probabilistic corresponding output neighborhood. So you try to match these probability distributions to find your solution for the dimension reduction. If you do that, if you organize these so that these probabilities become close to each other, then a number of methods have tried to do exactly that. One famous method was stochastic neighbor embedding, which basically matched these probability distributions by a KL divergence from the high dimensional to the low dimensional distributions. And then a T-distributed version, TSNE, continues to be extremely popular all over. That's basically almost the same as SNE, but with some slight modifications to use a different type of distribution in the low-dimensional space. Now, a further modification or analysis said that, okay, how about instead of just treating these divergences as mathematics, can we find some task-based interpretation for what they are doing? And it turned out that it was possible to formulate this reduction as an information retrieval task. And it turned out that by analyzing it like that, you could find that there are different solutions. Yes, different solutions. I'll hurry up to finish. And then these solutions yield the need for different kinds of criteria to match different kinds of errors. Basically, precision and recall turned out to be the two information retrieval criteria. And you could formulate them as two different divergences, not just the one used in SNE or TSNE, but also another one that is here on the right side of the screen. And the neighbor retrieval visualizer was a method that did that. Now, there's a recent extension in EuroVis 2020, which takes into account categories of data and then further says that, okay, these two divergences, we can further do it within classes and between classes to emphasize different preservation for each. That gives out some nice results. And you can use these solutions, the neighbor embedding solutions, in different kinds of interfaces. This is an interface which shows documents visualized with a neighbor embedding approach, which you can then zoom into and analyze, and you can have various kinds of linked views in there. Another solution is that you are actually analyzing a model, not data, but a model that is built to represent a user's information retrieval interests. And then for this, you could create a visualization like this, where the model is actually shown as a cloud of model features. So these are actually features that affect the model. And with this, you can then create an interactive interface where the user can explore hundreds of features that affect the model, and then they can explore them in an organized fashion. And then very recently, there has been developed versions where you can do multiple explorations at the same time. This is coming out later this year. Wrapping up, we have methods from linear to nonlinear, which started from maximization of simple variance statistics to preservation of neighbors. And all of them maintain this probabilistic approach of what is important to preserve. Once you can define that, you can build them into good methods for dimension reduction and then into visual interfaces. That concludes the very brief wrap-up.
Thank you very much, Jaakko, for your interesting talk. I think we have time for about one question. We have one already in the Discord. So thank you for your talk. A very interesting summary. What are some good ways to reduce overlapping / cluttering in 2D embeddings without ruining the representation?
This is a very crucial question, and it's not as easy as one might think, because the question you need to ask is that, is the clutter real, or is it just an artifact of the dimension reduction? If it's real, then it's an actual property of the data that you should be seeing. I point this out because there are some methods that divide the data into things that look like nice groups, but actually this division is not real. It's an artifact of the dimension reduction process. So some methods that give you things that seem like nicely clustered data, but it's just a fake clustering, which is not coming from the actual original data, but it is an artifact of the process. So in some cases, these methods like the use of T-distributions in TSNE is an approach that can enhance separation between existing clusters where they exist. But there's a danger that sometimes they do it also in cases where there isn't a real separation. So you kind of always have to be wary of whether what you are seeing is real. So I would also always couple these plots with actual quantitative analysis of these, for example, these precision recall curves, just to make sure that the separation that you are seeing is matching something real in the data. So so this is something like a caveat that you have to take into account. So if you are willing to accept that, then what you could do to reduce overlap, to reduce clutter, well, I would bring in the annotation, use the supervised methods when they are available, because they can tell that what is the most important set of divisions that the method should try to preserve. That makes things easier to show the essentials of the data. I would also use these t-distributions when possible, but being wary of the possibility of artificial divisions. And then lastly, I would bring in interaction that the user could really explore and say that, oh, these connections, they are not important for me to see. You can keep these further away from each other. These don't need to be so close to each other. So that way, there are some interactive methods that allow you to do that. So that way the methods could learn that which of the many similarities and dissimilarities need to be shown at the same time, because it's always a trade-off. You can't show everything, you can't show every detail correctly. When you tell the method, it becomes easier to make the right trade-off.
Okay, thank you very much, Jaakko. I think we will have a presentation by myself for just under 10 minutes. I think I can do it fairly quickly. We're running a little bit over time, but that is okay. For my session, there will not be a Q&A at the end, but you can definitely type questions into the Discord and to the YouTube live chat, and I will answer them in written form. So for the final talk, I will be giving a brief presentation. Okay. Am I okay? Yes. Sorry. Hold on. Thank you very much. This is Daniel Archambault, and I'll be presenting on visual analytics solutions for compartmental modeling in response to COVID-19. This was a project undertaken with many researchers at Swansea University, including Alma Riat, Tom Torsten Möller, Roger Fabro, Finlay Gibsons from the University of Exeter, myself and Biagio Lucini and Michael Gravenor, Biagio in the mathematics department at Swansea and Michael Gravenor as part of the medical school. Okay, so during this time period, we decided to try and work with people in compartmental modeling to try and provide predictions for hospital bed usage in response to COVID-19. So in general, the approach is to predict this usage in the short term. And the solution that was in use was you have your measurements for how many patients are coming in, and you fit a linear model and an exponential model to that data, and the future you estimate future solutions as lying in between these regions. However, our collaborators had a desire to have a more epidemiologically grounded approach. And so as a result, we used a simple tool and a simple model for this. The grounding was in an SEIR model. And we use this model, we fit this model to the data, and then we produce a prediction 14 days out. And the idea here was we wanted a very simple model so that it's quite explainable. And on the other end, making exploration also quite explainable as well. So no complex models here. So firstly, you might not know what compartmental modeling is. Compartmental modeling is an epidemiological way of dividing the population into several compartments, and they progress through these compartments to simulate disease spread. In terms of how the population moves between these compartments, you have a set of differential equations on each of the edges, and that'll tell you where people go from left to right. And each of the compartments roughly corresponds to a state of the disease in the community. So in the case of predicting these hospital bed usage, we didn't really need a full or complex model. Instead, we use SEIR. So S is susceptible, E is exposed, I is infected, and R is recovered. So we've measured a bunch of data. The data is an estimate of the transition between infected and recovered in this particular case. And then you can use single or multi-objective optimization, which we did with Tom and Alma, in order to find solutions to this in order to find well-fitting solutions to this model. This is all subject to certain constraints. S plus E plus I plus R would roughly need to correspond to the population of Wales. And also you could produce certain constraints on some of the compartments. So for example, at a particular time, we may think that 0.3 of the population has been exposed, well, has been either recovered or passed away from the disease. Okay, so once you do this this optimization approach, you have essentially a state of the compartmental model, and you can run this forward 14 or 21 days in the future to get an estimate of future admissions. And so here was our initial prototype, which is still under work. So here's a linear fit of this data. So in this case, the admissions are declining. And then the fit of the compartmental model is here. So you have the best fit that minimizes error, and this dashed line indicates when you start predicting. So that's the point where you take the compartmental model and begin to run forwards. Now, we've all been hearing things in the media about R. R is essentially how many expected infections are there from a person over their infectious period. You can adjust R, so you can estimate if R is higher or lower than what the model is predicting. You can have a light green line that will indicate how the model would look under that new contact. So in terms of future work, we are currently working on more complex models. In fact, Biagio Lucchini wrote the Welsh governmental model in order to make lockdown predictions for Wales, and we're looking at applying some of this to that. We hope to make disease modeling more accessible to policymakers through these visual analytics solutions. And sort of a little bit following on from Torsten's presentation earlier today, we are exploring multi-objective optimizations approaches for this. So for example, how do you balance disease and economic factors? So a little bit of a special thanks. This research was funded by the Welsh Government Sir Cymru 3 grant. And also thank you to RentVis, which is currently in progress. And we currently have a short paper at Gecko 2021, and you can go see that information here. Now, as mentioned previously, we will not be going to a Q&A version of this because we're overrunning a little bit. So we will transition into the break, and I will definitely answer questions on the Discord. And you can type them in either to YouTube chat or Discord, and you can see some of my answers there. Also, as a reminder, the links for YouTube and the channel in Discord will change between the two sessions. So please make sure that you click on the new link in order to access the new discussions and new videos. With that, I thank you very much. And after the break, hopefully we'll see you at MLVis, the second session, where we will have some paper presentations and a panel. Thank you very much.